network without needing to configure every single router individually. Segment routing components. In segment routing, SR, the network is treated like a series of waypoints. To guide a packet from start to finish, the source router breaks the journey down into specific components. These components are represented as segment identifiers, SIDs. Node SID, prefix SID. The node SID is a global identifier for a specific router, node, in the network. Role, it represents the shortest path to that router. Scope, it is global, meaning every router in the network knows that SID 16001 refers to router A. Analogy, think of this as a city name on a highway sign. If you follow the signs for New York, you will take the most direct highway route to get there. Adjacency SID, adjective SID, the adjacency SID represents a specific physical link between two neighboring routers. Role, it forces a packet to cross a specific interface, even if it is not the shortest path. Scope, it is local, meaning only the router that owns the link cares about that specific ID. Analogy, think of this as a specific exit number or a turn right on Elm Street instruction. It's a very specific local movement. Service SID. A service SID is a specialized instruction that tells a router to send a packet to a specific function or service before forwarding it further. Role, it enables service chaining. The packet can be steered through a virtual firewall, a deep packet inspection, DPI, engine, or a video optimizer. Deployment, this is most common in SRv6, where the function part of the IPv6 address tells the router exactly what service to apply to the packet. Analogy, think of this as a pit stop or a stop at the dry cleaner's instruction during your trip. Segment list, the stack, the segment list, often called a SID stack in MPLS, is the ordered collection of SIDs that defines the entire end-to-end path. Structure, it is an ordered list placed in the packet header. How it works: 1. The packet arrives at a router with a stack of SIDs. 2. The router looks at the top SID. 3. Once that instruction is completed, the packet reaches the node or crosses the link, that SID is popped, removed, from the list. 4. The next SID becomes the new instruction. Summary table of components. Component identifier, SID, scope instruction node SID global go to router X via shortest path. Adjacency adjective SID local cross this specific link. Service SID local / global process this packet through firewall Y. Path segment list path Y the full turn-by-turn itinerary. Why these components matter: by combining these, an SDN controller can build a very complex path using a simple list. For example, a list could say, 1. Use the shortest path to node A, node SID. 2. From node A, force the packet over link 1 to avoid congestion, adjective SID. 3. Send the packet through the firewall, service SID. 4. Use the shortest path to the destination, node SID. SR versus traditional MPLS traffic engineering. Comparing segment routing, SR, with traditional MPLS traffic engineering, MPLS-TE, highlights a major shift from stateful networks to stateless ones. While both technologies aim to steer traffic along paths other than the standard shortest path, they go about it in fundamentally different ways. Key comparison matrix feature: traditional MPLS-TE, RSVP-TE, segment routing, SRTE, control RSVP-TE, complex signaling, IGP extensions, OSPF/ISAs, protocol stateful, every router in the path stateless, only the entry router knows path state must store information about the path, others just follow header tunnel. Instructions. Low, routers struggle with scalability. Very high, supports millions of flows, thousands of tunnels. Configuration manual and complex. Highly automated via SDN. Fast reroute, FRR, complex to protection TILFA, simple, 100% coverage. Setup. Data plane MPLS labels only. MPLS or IPv6, SRv6. Signaling and complexity. Traditional MPLS-TE relies on RSVP-TE, resource reservation protocol. It's like a keep alive system. Every router along a path must constantly talk to its neighbors to maintain the tunnel. If one router forgets the state, the tunnel collapses. Segment routing does away with RSVP-TE entirely. It uses simple extensions to existing routing protocols, OSPF or ISAs, to distribute labels, SIDs. There is no signaling for specific paths. The path is simply written into the packet header. Scalability, the state problem. Traditional MPLS-TE, because every router must maintain the state of every tunnel passing through it, the midpoint routers get overwhelmed as the network grows. This is why traditional TE was usually limited to the network core. Segment routing, the midpoint routers are dumb. They don't know they are part of a traffic engineered path, they just see a label /SID and swap it. This allows SR to scale to massive data centers and carrier networks. Path protection, resiliency, traditional MPLS-TE uses fast reroute, FRR. It is effective but very difficult to design because you have to manually configure backup tunnels for every primary tunnel. Segment routing uses TILFA, topology independent loop-free alternate. Point 2 Because the SDN controller or the router has a global view of the segments, it pre-calculates a backup path for every possible failure automatically. 3 It guarantees sub 50 ms recovery regardless of the network topology. Integration with SDN traditional MPLS TE, it is difficult for an external controller to manage RSVP TE tunnels because of the distributed nature of the protocol logic. Segment routing, it is the native language of SDN. An SDN controller calculates a path and simply gives the ingress router a segment list. The controller doesn't need to touch any other router in the network to make that path work. Summary, why the shift? Modern networks, 5G, cloud, and AI, require millions of individual traffic flows with different requirements, latency, bandwidth, etc. Traditional MPLS TE breaks under this load because of its stateful nature. Segment routing is the preferred choice for 2026 because it provides the same control as traditional TE but with the simplicity and scale of the standard Internet. Applications of segment routing in 2026. Segment routing, SR, has become the universal transport across multiple network domains. Its primary value is its ability to provide high-performance traffic engineering without the complexity of traditional protocols. Here is how SR is applied across various networking areas. 1. Carrier backbones, core scalability in massive service provider networks. SR is used to replace legacy MPLS TE. Stateless core, carriers can support millions of concurrent traffic flows. Because the core routers don't need to store tunnel state, the backbone can scale indefinitely. TILFA, protection carriers use topology independent loop-free alternate to guarantee that if a fiber is cut, traffic reroutes in less than 50 milliseconds. This works regardless of how complex the network topology is. Unified fabric, it allows the carrier to run a single protocol from the access router at the cell tower all the way through the core to the data center. 2. Data center interconnect, DCI. DCI links high-capacity data centers over long distances. Low latency steering, SR allows a provider to identify latency-sensitive traffic, like high-frequency trading or AI synchronization, and force it onto the physically shortest fiber path, while bulk data backups are pushed to higher latency, higher capacity links. Smooth integration with IPO-DWDM, as discussed earlier, SR provides the IP logic to steer traffic across the colored wavelengths provided by IPO-DWDM routers. 3. 5G networks, network slicing. SR is the foundational technology that makes 5G network slicing possible. Hard and soft slicing, by using different segment lists, a 5G operator can carve out a slice of the network for autonomous vehicles, ultra-low latency, and another for mobile broadband, high throughput. Flex algo, operators can create flexible algorithms where a specific SID, segment ID, represents a path that only uses links with specific characteristics, such as only links with MACsec encryption. For virtual private networks, VPNs, SR simplifies how BGP-based VPNs, L3 VPN and eVPN, are delivered. BGP-SR integration, in traditional networks, you needed LDP or RSVP to carry VPN labels. With SR, the VPN labels are simply stacked on top of the SR SID stack. Seamless connectivity, it enables eVPN, Ethernet VPN, to operate more efficiently, providing Layer 2 connectivity across a Layer 3 SR backbone with much faster convergence during failures. 5. Service function chaining, SFC, this is one of the most powerful applications of SRv6. The instruction header, in an SRv6 network, a packet header can contain a list of functions. Automated steering, a packet can be instructed to, 1. Go to the firewall, service SID 1. 2. Then go to the intrusion detection system, service SID 2. 3. Finally, go to the destination. Efficiency, this removes the need for complex VLAN stitching or physical cable loops to force traffic through security appliances. Summary of applications area key SR benefit preferred data plane carrier backbone scalability and fast reroute, TILFA, SR MPLS data center /DCI low latency and AI optimization SR MPLS /SRv6 5G networks network slicing SRv6 VPNs protocol simplification, LDP removal, SR MPLS SFC programmable service steering SRv6.